with the first talk from Hendrik Brückler, who is a PhD student in the University of Osnabrück. So, please.
Yeah, hi. Thanks so much for the introduction. So, my talk today will be about integer sheet pump quantization for hexahedral meshing. So, the method we present here is part of the integer grid map hex meshing pipeline. Hex meshing is a notoriously hard problem, and simply put, one needs to decide how many vertices to generate, how to connect them, and where to put them. And this is a mix of discrete and continuous degrees of freedom, and usually deciding all of them at once is practically impossible. So the integer grid map pipeline, therefore, divides this task into several steps, and each step only decides some of these degrees of freedom. To see where our method fits in, we need to take a closer look at the individual steps. The first step is the definition of a smooth frame field over the volume. The frame field determines the location and types of singularities, and these will become irregular edges of the later hex mesh. Additionally, it prescribes alignment of cells. So hexahedra will be aligned later with the frame field streamlines. In the next step, the domain is cut, driven by topology and singularities, and then mapped onto a grid. The grid pre-image then fills the domain and is aligned with the frame field. But it is still discontinuous along cuts and does not line up well with boundaries nor features. To achieve this, features and boundaries need to be snapped to grid corners. And assuming a unit grid, this corresponds to snapping the map at boundaries and features to integers. Hence the name integer grid map. This step, however, the snapping, is not trivial. The choice of integers here is called quantization, and is what our method is concerned with. This, to be sure, is not the same kind of quantization we heard about yesterday in the compression talk. Until quite recently, the go-to method for quantization was simple rounding. However, as quantization is a problem with complex constraints, this naive approach often fails, as you can see here. About 2 years ago, we proposed a robust method based on solving a series of integer quadratic programs, or IQPs for short. This method builds a block partition on the input and then assigns consistent integer sizes to these blocks, representing the number of hex sheets crossing the blocks in the later hex mesh. The main drawback of this method is its dependence on integer solvers, which are expensive in at least one aspect you can think of: time, money, ease of use, or more. The method we present here is basically a replacement that is also reliable, is near optimal, but mitigates all the issues of using integer solvers. To introduce all formalisms relevant for our method, I will start with a short recap of quantization problems. Quantization has been treated first for quad meshing on surfaces. Just like in the volume, the points of interest here are singularities, boundaries, and features. And we will refer to any of these simply as features in the following. These features are spatially fixed throughout the remeshing process, and that makes them ideal reference points for prescribing numbers of layers of quads to be inserted in between them. And these number of inserted layers can be represented as integer spacings. To then constrain all features relative to each other, they have to be embedded in some coarse global network. An established structure for that purpose is a quadrilateral partition of the surface called motorcycle graph. And this partition has T-shaped junctions between patches and is thus referred to as a T-mesh. In the volume, the process is the same. Between all features, integer spacings can be prescribed on the basis of some coarse global network. And for this network, we previously introduced a volumetric T-mesh structure that is also the structure we will be using here. This structure is composed of arcs, quadrilateral patches, and cuboidal blocks. On the structure, the quantization is represented as a bunch of integer crossing numbers, one per arc. And those prescribe how many hex sheets in the output should cross each arc. So a hex sheet in the result could look like this. Then satisfying all the crossing numbers yields the final hex mesh. At first glance, this might seem like a simple subdivision scheme of a conforming partition without T-junctions, but a closer look reveals more complex interactions. Here, for example, the 0 is needed for optimal feature alignment. On a more complex example, with more T-junctions, again, quantization is responsible for a proper alignment of features. For now, we switch to 2D sketches for visual clarity. A valid quantization has to satisfy some constraints. The first is that of consistency. It requires that opposite patch sides be of equal length, and length here refers to the sum of crossing numbers. Consistency prevents situations like this that cannot be resolved locally without additional singularities. Also, we need to require separation of features by at least one sheet passing in between them. Otherwise, a situation like this, with two features in dark green, would result either in holes in the output or in loss of features, and neither of this is acceptable. To then formalize this, we simply stack the arcwise integers into a vector and translate the consistency constraints into a linear equation system and the separation constraint into a system of linear inequalities. Most importantly, though, the hex meshing problem involves target lengths for each arc. These usually come from the solution of the previous continuous version of the grid map problem. The global goal is then to minimize deviation between continuous target lengths and the quantized integer lengths. We assume that the target numbers have been chosen sensibly and carefully because then the quality of quantization is fully described by the faithfulness to these targets. Formulating all this as an integer quadratic program, or IQP for short, is now straightforward. So the objective is to minimize quadratic deviation from target numbers, such that both consistency and separation of features are maintained. Our previous method employed a general purpose integer solver to solve this IQP, and this yields optimal results given enough time, but has the issues discussed before. Our new method can reliably solve the same problem quickly and near optimally, but without daunting dependencies. What I've shown you so far was just a general recap of quantization problems. And starting here, I will start to talk about the specifics of our method. The idea of our approach is to start from some initial quantization. In that quantization, we can identify arcs that are far away from their target values. We then look for virtual sheets in the quantization that we can inflate or deflate to improve these arcs. These sheets are represented as groups of integer deltas. Hence, we call them integer sheets. Using these sheets, we can iteratively pump the bad arcs towards their target. And this integer sheet pumping is then simply repeated greedily until no more improving update can be found. The question then is, of course, how can we determine useful integer sheets? Some effort is needed to guarantee that they are feasible, but above all, they need to be good and flexible updates. So ones that can push us towards optimality as straight and as reliably as possible. So first, the updates should preserve consistency of the quantization, which we've seen before. In 2D, this can be secured by updating not isolated arcs, but all arcs in closed paths on a dual arc graph. So to update the blue arc here, a path crossing it is required. This path then corresponds to a consistent integer update. Here it even represents a virtual quad strip inserted into the quad mesh to be. Also, we want to find updates that bring our arcs closer to their targets. And in 2D, one can assign certain weights to arcs so that a good quantization update then corresponds to a minimal weight path in this graph. So here, a simple Dijkstra algorithm can be used for finding good updates. In 3D, the arc graph has an additional dimension, and the closed path analogy does not work. Instead, what is needed here is basically a closed surface in a dual cell complex. And such a minimal weight surface in a discrete mesh can be found by linear programming, requiring integer solutions. Of course, if that were all, nothing would be gained, as we would still need an integer solver here. So the crucial insight here is that already the continuous relaxation of this integer LP has an integer optimum most of the time. And in case it doesn't, a reasonably close integer solution is easy to find. So the linear program to find us such quantization updates we formulate as follows. The objective function is the total unfavorability of an update, which of course is to be minimized. The solution is then the least unfavorable update or the most favorable update. For this, we assign arc weights that represent how unfavorable updating that specific arc is. And recall that arcs have both a target and a current length, and the update will be applied to the current lengths. So this defines 3 tiers of arcs. The lowest weights are assigned to favorable arcs. The update will bring those closer to their target. Also, for other arcs, the update might make little difference or even increase deviation. So we give those a higher unfavorability score. A solution will then generally contain as few updates as possible and favor good updates over bad ones. And these updates, again, are subject to the consistency and separation constraints. As is, a 0 update would trivially be the least unfavorable or the optimal solution. So to get a meaningful result, we choose the single arc that is farthest away from its target and enforce a non-zero update for that. The properties of this LP are now mostly determined by matrices A and B. So these matrices by construction contain only zeros, ones, and minus ones. And those are integers, so our LP constraint polyhedron has only rational corners. And because the classic simplex method explores exactly these corners, it will always find a rational optimum at least. We also observe that the matrix subdeterminants are mostly, but not exclusively, from 0, 1, and minus 1 as well. And we conjecture that this is the reason that the continuous optimum often is already integer valued. Consider this example. So the pump condition inflates one arc, and the consistency constraints are responsible for inflating this into an entire sheet. In this and most other cases, the solution is already integer. There are some special cases, though. So here, if we propagate along the cycle, the sheet crosses the same arc twice. And the solution returned by the LP would then contain half integers. So still, any non-integer solution can still be made integer by multiplication with the lowest common denominator. In 2D, this is at most 2, as seen in this example. Adding a third dimension, however, allows the nesting of such structures, and as a consequence, LCDs can become unbounded. So imagine an extrusion of this for a proper volumetric T-mesh. This here is more of a theoretical construct, though, and in practice we have observed much nicer distributions of LCDs. So overall, 95% of our LPs directly yield an integer solution, and in most other cases, multiplication only by factor 2 is needed. Higher factors basically occur only very rarely. Okay, so what can these sheet updates we determine actually do? First of all, they can model inflation of sheets, but in the same way can also represent deflation. And these two images might remind you of hex sheet insertion or removal operators that are sometimes used in hex mesh post-processing. And for these simplistic examples, there sure is a strong connection, but it is important to note that in general, our integer sheet operators are more powerful than hex sheet operators. And to see why that is the case, consider this example. So the top row shows a quantization and the bottom the corresponding output mesh. And how do we go now from this configuration to a similar one shown on the right? So we can handle this transition with just a single integer sheet. But trying to insert such a sheet directly into the hex mesh does not work. So instead, working on the output mesh requires more operations to achieve the same output. 3 to be precise. So our integer sheet operators are much more useful in a greedy approach where bad intermediate states cannot be tolerated. Speaking of bad intermediate states, let's consider another example. So this is again the same partition, but now with explicit target numbers highlighted in gray. Say we have this current quantization with inscribed objective value. Ideally, we'd like to go directly to the optimum. However, if we try to get there, just a second, try to get there by inflation first, this increases total deviation and will thus be rejected by our greedy approach. Instead, trying deflation first, does not work either, and that's for the same reason. So what is needed is a way to combine inflation and deflation in a single step. And this corresponds to a sum of inflating and deflating sheets. And a sum is also exactly how we can model these mixed sign sheets in our objective function. So note that our update variables down there have to be non-negative for our LP to not be unbounded. We can split this into a sum of terms with one representing inflation and the other one deflation, but still both types of variables still being non-negative. In this way, we can include mixed sign sheets into our LP. Now that we have fine-tuned the sheet operators, all that's left to do is embedding them in some greedy optimization scheme. So we start with a zero quantization. This zero quantization is trivially consistent because all opposite patch sides are of equal length. But separation is another matter. So a zero quantization cannot separate any features. Our algorithm actually enforces separation only as needed. So what that means is, instead of starting with a complete set of pairwise separation constraints for features, we start without any and then add them only on demand and on the fly. Doing this keeps our inequality system lightweight for our LPs. So after initialization, we repeatedly use our LP to find updates that reduce the deviation from targets and apply them to the current quantization. This then is repeated until no more improvement can be found. As we have not yet explicitly separated features, we might find some unseparated ones after optimization. And then for each pair of unseparated features we find, we use our LP to find a separating update and then apply that directly to the quantization. And this is finally repeated until no unseparated features remain. Because these new constraints might change the global optimum, we still have to repeat optimization until both the objective and the separation are no longer changing. That's basically everything required for our method. For more specific details, I have to refer you to the paper. So for now, here's how our method works in practice. Both our algorithm and the previous IQP method are anytime methods. They produce intermediate solutions that can be retrieved at any time. So instead of considering only the final objective value, we consider also intermediate values over time. So a curve will generally look like this. Before the first feasible solution is found, we can consider the objective value infinite. So then a first solution is found and improved until finally the algorithm terminates. And the characteristics are the final objective value, the time when it is obtained, and the final termination time of the algorithm. We measured such plots for about 1,300 test instances from 2 data sets that were also used in previous quantization papers. And we processed these data sets with both our method and the previous method based on IQP solvers. For a first analysis, we want to average all these 1,300 plots for each method. For this, we invert the y-axis, so this makes it a relative optimality. 0% means infeasible, and a 100% is the final value of the optimal IQP method. We also normalize the time axis so that it is relative to the time when our method reaches its final value. The result of averaging the plots like this is shown here for our method. So then comparing our average curve to the one obtained with an open source IQP solver already reveals that our method achieves high optimality levels much faster. It is eventually surpassed slightly by the IQP solver, but the time gap to break even is quite large. Of course, one could invest also in a commercial solver to speed things up. But still, even the commercial solver cannot catch up in terms of speed. For reference, the open source solver used here is Bommes, the commercial one is Grobi, and for our LPs, we employ CLP. For another comparison, we look at the performance of not processing just a single model, but a whole data set sequentially and looking at the accumulated model-wise termination time and optimality. So this is the curve for our method. It takes about half an hour to process the whole data set, and in the end, total optimality is almost 100%. Because the branch and bound integer solver will generally spend large amounts of time to prove optimality of the solution, we allow it to stop before reaching full optimality. But even so, it takes the solver almost an entire day to finish the whole data set. Its final optimality is slightly higher than ours. If we instead employ a time limit of 20 seconds for that solver, processing time does go down, but so does the optimality. So our method surpasses this configuration in both terms of speed and optimality. So far, we have considered optimality just as the abstract deviation from some target lengths. So to tell how much this gap actually matters in practice, we should look at some hex meshes produced from these quantizations. So first of all, the average case. For such small optimality gaps, one can hardly spot a difference between the two meshes. Actually, even for bad cases, it is surprisingly hard to spot the difference between meshes. A difference in actual mesh quality is rather rare. For the final analysis, we also want to compare termination times of the algorithm. In this aspect, integer solvers are usually notoriously hard to predict. So we look at the termination times as a function of input complexity represented by the number of variables of our problem. Our method shows nice behavior, never takes more than 100 seconds to finish on any instance, and exhibits a low maximum spread. The open source solver instead does not behave as nicely and varies greatly in runtimes. So we had to even enable a generous 5-hour time limit, and it is impossible to say otherwise how long it would have taken the solver to terminate on some instances. As a result, the maximum spread is quite high here. Lastly, one would hope that a commercial solver could alleviate some of these issues, but actually, even here, it doesn't. So the commercial solver runtimes explode just as unpredictably for larger inputs. To conclude your results, here's one more round of spot the difference. Yeah, I think this is unclear, but maybe if we can highlight the mesh's underlying structure using the base complex to reveal the high-level structure. But again, the differences are hardly noticeable, and generally, they don't really result in worse mesh quality. Even for coarse meshes, there is no evident advantage of using the slower IQP method. Okay, time to wrap things up, I think. So our new method is predictably fast, does not require costly dependencies, and is open source only. Code will also be made available shortly on GitHub, and it will also be integrated into the front-to-hex meshing pipeline of AlgoHex. In terms of optimality, of course, our method is not perfect, but I think we have shown that it is still usually sufficient in practice. Eventually, the quality of a quantization can, of course, only be good as its objective function, and quadratic deviation per arc has been a practical choice for this. It is easy to implement, it plays nicely with integer solvers, but whether it is actually the best choice for a more flexible iterative approach is more of a question for future work. All right, thank you very much for your attention.
Thank you for a very insightful presentation on a brave subject such as hex meshing. Are there any questions from the audience first? Yes.
Thanks for the talk. I was wondering, how specialized is this technique for your hex meshing quantization problems? Like, could I just take any IQP and apply this kind of splitting and solve these LPs to solve it? Or
It looks like it could be applied to a lot of problems that have a similar structure, right? I mean, a requirement would be that your problem should have this property that it usually has integer solution even in the continuous sense, right? If you find some proper objective function for your LP, and the constraints then should allow for it to often find integer solutions to be useful in the same way this is. But yeah, it should work for other problems as well.
thanks.
Any more questions from the audience? Yes.
Nice talk, thank you. I think I just missed something. It seems like your objective is how close the quantized values are to the original values.
Exactly.
But your function, your optimization seems to be monotonic. But it seems like when you introduce this separation, satisfy the separation constraints, you can actually make the energy go back up, right?
Yes, but that is included in the infeasible region we've seen in the plots. So until the final iteration where we can guarantee from now on it is actually separated, we consider it as infeasible, which we just assign an infinite objective to.
Yeah,
So
thank you.
in that sense, it gets monotonic afterwards.
More questions from the audience? Okay, I'll ask a question that is a little bit like a follow-up. Since your algorithm is essentially not like a one solution like this IQP, but kind of iterative, can you find situation where it kind of zigzags? Because you do this inflation deflation, so you add the delta x and then remove the delta x and then you go back and forward?
So you're thinking of some infinite loops?
Yes, to get kind of stuck in your algorithm because you keep hovering around the energy and not making actual progress.
I don't think that's possible because we truly proceed only greedily. So we only allow some updates that that actually reduce the global objective function of the IQP. So the deviation, if an update does not reduce this deviation, we do not allow it. So in that sense, I don't see how that would be possible.
Okay. And in a related note, can you find, so in a single situation, yes, you can have those rational coordinates and you introduce a lot of quads, but the iterative situation, can you find a situation where you keep pumping more quads into one edge or something like this, and then the rest are kind of neglected because this reduces the energy more? This is something that can happen?
We have not seen such an example in the data set we processed. I don't think this should be a situation that occurs in practice, but I cannot for sure guarantee that it can never.
Very pathological singularity is like something that is a triangle that just adds up quads or something like this.
I can't say more to this answer.
Okay.
I don't think it can occur, but I don't have a proof right now.
Okay, maybe last question from the audience, if there is such. Yes.
Can you combine the two, that you use your method to get forward quickly and then you switch to the other one which leads to a better result? Or would you introduce too much error in the first part?
No, absolutely, you can combine these two. So you can just use our fast method as a heuristic, basically before for a warm start of the IQP, and this totally works. In our experiments, we did not see any improvement in terms of final objective value for this, but of course it might speed things up. Yeah.
Okay, so let's thank the speaker again. Okay, just with a little delay. So Lance Simmons will present here the work with Nina Amenta from UC Davis about one of my favorite subjects, CrossFit.
So today, I want to talk about a precursor to quad meshing, specifically creating cross fields. Typical pipeline for quad meshing typically starts with some information in the plane, so some sort of constraints. So here's an example. We're going from a small feature size in purple, growing until it gets larger in the yellow area. From these constraints, we try to generate a cross field that we want to be as smooth as possible while honoring the constraints. And then from the cross field, we can extract quad mesh, and ideally we want all of the edges in the quad mesh to be streamlines in the cross field. So today, we're going to focus just on this first step. So if the size constraints we had to start with are growing from like a 1 to 4x growth, then we can say this is a good cross field because we can generate a mesh from the cross field that matches our constraints. If this was a 1 to 40x growth, not so much. What we'd like to be able to do is analyze just the cross field without having to generate a mesh to say whether or not the cross field matches our constraints. This work was motivated by groundwater flow. So this is the Sacramento Valley in California. The constraints we're working with are just size, but there are plenty of other constraints that will actually end up having pretty much the same impacts on the resulting fields. So hopefully, I can convince you guys that there's still useful math to be done in the plane. So generally, when we're trying to generate a cross field, we're starting from the perspective of trying to make it isotropic. So if we have our normal Euclidean metric in a UV plane, we conformally map it to our XY plane where we want the cross field, and that gives us an isotropic metric in XY. So that's, that's kind of the definition of a conformal map. However, we have iso lines in our metric space that become curves in XY. And these curves are the lines that eventually we want to be quad edges. As we refine, the iso lines stay the same, but as the elements get smaller, the quad edges get straighter and straighter. So as we refine, we get these tiny little bricks that even though the iso lines are curved, they look locally straight. And we can even go a step further and refine to the point where we have no area left. So all we have is just direction or orientation. So that gives us just a cross field that we map to a cross field. And here, we know this cross field emits an isotropic metric because we started with one. But in all cases, we don't know if that's true. So we have to start from a more general perspective here. So we're going to look at an arbitrary map M that's, we know it's orthogonal, but we don't know if it's isotropic or not, so we're assuming anisotropy. So we have our UV metric space that we're mapping to XY. And in particular, we don't know if M is conformal or not, but we actually want to look at the Jacobian K, which is taking, it's a linear approximation of the tangent plane, and we want to look at how that behaves. So again, I mentioned that it's an anisotropic map, so at every point we have two size values along the axes. So we have a sigma and tau, and here we can see that sigma and tau are multiplying column vectors. So the change in sigma and tau are actually representing field-aligned stretch. So we're taking squares in our metric plane and mapping them to rectangles in our actual real space. And ideally, what we'd like to do is dissect the Jacobian and come up with a relation between the elements, but unfortunately, those are all expressed in terms of U and V. So if we look at the inverse instead, ignoring the map we started with, we can look at the Jacobian of the inverse map by just taking the inverse of the Jacobian of the forward map. So here we see that we have 1 over sigma and 1 over tau are multiplying across the rows, meaning we have an axis-aligned stretch. So squares in our XY space are mapping to parallelograms in UV. But importantly, all the terms are now functions of xy. And we can exploit the symmetry of second derivatives here to come up with relationships between the partial derivatives of the elements of our inverse Jacobian. And if we do that and then clean up, we get these two equations. So they're directional derivatives of sigma and tau, and ignoring what they are for a moment, we originally took the long route to get here. So we were working with Noppel et al.'s globally optimal direction fields, and we got the same result by relating the metric to the gradient or the curvature of alpha through the Levi-Civita connection. And as it turns out, we're in good company doing things the hard way, because just last year at IMR, or the International Meshing Roundtable, Jedzminovic et al. Gave some work where they derived the same equations by defining a Lie bracket and requiring it to be the zero vector. So they get the same result, but again, they had to use much more advanced math to do it. So we're hoping that just by looking at the inverse Jacobian, we have a slightly easier way to understand the math we're looking at. In practice, a lot of the cross fields we come across are not isotropic. So what we'd like to do is for any given cross field, we'd like to measure the, how far it is from an isotropic metric. And in particular, the question we want to ask is there always some orthogonal anisotropic continuous metric that you can find for any given cross field? So the general intuition of these two equations are defining how chords in the cross field grow. So in particular, we notice that both of them are directional derivatives in the direction either along orthogonal to alpha, but they're proportional to grad alpha in the perpendicular direction. So just to go back, sigma is the length measure in the direction of alpha, and here we can see that sigma changes when we take a step orthogonal to alpha. So along any field line, orthogonal to the direction of the field, alpha or sigma is the growth or the width of that field line. And similarly, tau is the measure orthogonal to alpha, but it changes as we move along alpha. So tau is also the width of field lines. So the difference between sigma and tau is just the direction of the field line you're traveling along. So here we can see we have grad alpha in red, and we have two field lines going underneath in blue, and we see that grad alpha actually has some curve to it. So we know grad alpha is non-zero, but in particular, as grad alpha increases, as that curve gets stronger, we would expect that the two blue field lines to be pulled further and further apart, causing all of the streamlines in between them to fan out and widen. So here we can see directly that the width of the field lines increases as you move across grad alpha. So to drill down just a little bit more, starting at some point P, if we move along the direction of alpha, we see tau is making that change. The directional derivative here says that the gradient of tau is changing as we move in that direction. But as we're moving along alpha, it doesn't say how sigma is changing. So we have one directional derivative enforcing tau, and sigma is free, and then if we move in the other direction, it flips. But as we keep moving in the same direction, the same rule keeps applying. So if you make a step in the alpha direction, tau is going to change, but at the new point, you have a new grad alpha, but you're still moving along tau. So if we were to specify some value for tau at point P, we actually specify values for the entire streamline in both directions, because you can integrate tau grad alpha from that starting seed point. So basically, if you specify a width anywhere along a streamline, you specify width everywhere along the streamline. So I want to go back to our earlier question. Is there always an orthogonal, anisotropic, continuous metric? And for that, we have a partial answer. If you allow these three restrictions, in particular that we do not specify the width at region boundaries, that streamlines must be finite, and that there can only be one singular point along a streamline. So in particular, that means separatrices start at a singularity and end at the boundary. With those restrictions, we can construct a continuous sigma and tau over the entire region. We start by specifying sigma equals tau equals some arbitrary value at each singularity. And then using the earlier directional derivatives, we can integrate that all along each separatrix, all the way to the boundary. So the values are changing proportional to grad alpha along the way. So a chord is a sequence of quads joined at opposing edges, but you can also think of it as a bundle of streamlines that are all moving together through the region. So if we look at this highlighted chord, every streamline in the chord is crossed by this purple line. Now, based on our earlier construction, we have width values at either end of the purple line. So we can choose an arbitrary smooth, as long as it's smooth, we can choose an arbitrary interpolation function to get values of sigma along the entire purple line. But, as I said earlier, if you have a value anywhere along a field line, you can integrate it out everywhere along a field line. This gives us a value for sigma along the entire chord. Not one value, a continuous value. So if you do this for every chord, because every point in the region is covered by two chords, that gives you a continuous sigma and tau over the entire region. So what we'd like to do is, instead of saying, it's possible with some arbitrary interpolation function, we want to give some degree of control over optimizing what sigma and tau are everywhere. So we want to start with a set of representative field lines that we can use for an optimization process. Now, if we start with the separatrix graph, shown in orange here, that's really good at capturing the topology of the region, but unfortunately, we run into some numerical difficulties, which I'll mention in a second. So we actually start with a collection of field lines that brackets every separatrix, shown here in blue. And what we want is to keep adding field lines until the region is sufficiently dense, where giving us a higher degree of control over the sigma and tau that we're optimizing for. So unfortunately, all of our growth is proportional to grad alpha, but as you get closer and closer to a singularity, grad alpha grows without bound, which introduces two problems. First, for tracing a streamline, if you're just doing forward Euler integration, it's possible to skip tracks and actually make a step that's too long and go in the wrong direction, so you're tracing the wrong streamline. But the harder problem is because grad alpha is increasing towards infinity, grad sigma and grad tau are also getting outrageously large. So trying to integrate sigma and tau along a field line is also really difficult. So for now, we don't actually use the stream or the separatrices when trying to compute sigma and tau. And unfortunately, that means that the optimization we're doing no longer gives you a smooth sigma and tau over the region. So we know it's possible to have a smooth sigma and tau. We're just not getting one yet. And the sacrifice that makes is not that the region is no longer meshable. It's just that the size function is discontinuous. So the little tiny bricks that all fit together to give us the mesh in the infinite or in the infinitesimal sense, the bricks all still fit together. It's just there's a discrepancy in the size. So here, going from left to right, the bricks get thinner and thinner and thinner, and then suddenly they're wide again. And that jump is the discontinuity. So I keep talking about anisotropy, and it's helpful to actually come up with a way to measure it. So the point-wise anisotropy metric we're using is sigma over tau plus tau over sigma minus 2 to some exponent. The minus 2 is just giving us a 0 energy in the case of an isotropic function where sigma equals tau. We want to raise it to an even power so that no matter what happens with sigma or tau, our energy function stays positive. And then k is just an exponent to more heavily penalize the worst anisotropy in the region. In practice, a k of 1 or 2 works really well. If you use a k of infinity, where your optimization process is just looking at the worst anisotropy in the region, this optimization gets caught in local minima. So we would actually advise not using a high k. And the optimization process is really straightforward. It's a greedy approach. We iterate over all of the streamlines in our representative set. We change the width of the streamline to minimize the anisotropy over all of the collisions it goes across. And we repeat doing this process until there's no further change. We know this is going to terminate because our anisotropy energy is non-negative, so you'll either hit 0 and you have an isotropic function, or you'll hit a minimum, or you might hit a point where the benefit from each iteration is minor enough where you can just terminate if the improvement threshold is too low. So I actually want to look at a data set where we measure the anisotropy. So I'm going to start with an NACA airfoil example. So this is a steady state airflow simulation where we've just normalized it and extracted the crossfield from that. In particular, we have 7 different singularities that in the back particularly, that's where the area of interest is. So we start off by trying to drop this representative set of streamlines, and we immediately run into a problem. Not only do we have limit cycles where streamlines are getting trapped in an infinite spiral of doom, but we also have 4 degenerate regions where the curvature is forcing streamlines to effectively merge together. And that's a case where the anisotropy grows to such an extent that that's no longer really useful to talk about. So we do a targeted relaxation around both of the singularities and these degenerate regions. Because the degenerate regions are a very rapid pi/2 rotation, you can compress that region so the pi/2 rotation happens over a small enough bound where you can just kind of ignore it. So by removing the 4 degenerate regions, The orbits of the two singularities no longer have those pi/2 rotations, so they drop from valence 0 singularities to valence 2 singularities, and the representative streamlines are actually able to cover the region. So when we zoom out, we see we have coverage over pretty much the entire region. We can optimize the anisotropy over, as we solve for values of sigma and tau over the region. And then within each of these rectangular regions, we can interpolate sigma and tau to come up with a per pixel anisotropy, which we then render. So a lot of the region is actually very close to 1-to-1, so isotropic, or close to it anyway. It moves down to an orange in the, where it's like 2-to-1, which is still very reasonable. But we have a couple of regions in the turbulent section behind the wing where we're getting as high as 192-to-1 anisotropy. And the real takeaway here is that while all of the turbulence is happening behind the wing, the anisotropy escapes. So when you have high anisotropy at a point, it ends up polluting both of the streamlines across it. So I would like to end with an open problem. In particular, the restrictions that we talked about earlier for a continuous size function are no longer reasonable restrictions to make in 3D. In particular, separatrices can't end at the boundary if there isn't a boundary. So asking our earlier question, if we have a layout of separatrices on a closed surface in 3D, making quads, so it is meshable, does it always admit a continuous orthogonal frame field? And it might be as simple as relaxing our earlier assumption where you can assign any size you want at each singularity. It might be only a subset of possible sizes. Or it might be as strong a requirement as needing a harmonic alpha function on the surface so that all loops over the surface integrate to 1. We don't know what the solution to that is, and we hope that's something that you guys are willing to chew on. So thank you for your time, and hopefully thank you for helping us save the bunny.
Questions from the audience?
Just out of curiosity, is there a reason it's important to keep the direction fixed as a hard constraint? It seems like in situations where you end up with extreme anisotropy, allowing the direction of the field to slightly deviate may significantly relax the anisotropy.
Yes, so we're starting with the perspective of trying to stick to the direction field as much as possible. In particular, in this example with high anisotropy, allowing the field to deviate, you can, with 192-to-1, you can very easily perturb the field to relax it. But it might also be, like if you didn't have to have a quad field, that would be an excellent point to just insert a triangle and reduce the rest of the chord. So you can do topological operations or even add singularities to redirect the chord. We're still investigating what the next step looks like, but in particular here, we have pretty much 4 or 5 regions with the most extreme anisotropy, and I figured, adding singularities to redirect those chords might be the best way to go here, as opposed to like the typical example of if you have an area that you want really fine resolution at, you have to have like a wall of singularities to go from your dense region to your high region. So I think it's promising that you don't have to add a wall of singularities. You can target it, but that also kind of implies that by generating the direction field, you're still not done placing singularities. There might be opportunities to really improve your mesh by adding more after the fact. So, thank you.
I'm going to use this as an opportunity just to help me understand your equation since you're here and it's easier than reading your paper. No, if you don't mind pulling up the equation with the grad alpha in it, I have a very simple question, which I just had a little bit of trouble parsing it. Yeah.
Okay.
So in particular, so alpha is an angle, right? So grad alpha is a vector?
Yes.
So then it's multiplied by another vector? Can you just help us parse this formula? I promise you it was a simple question.
No, that's totally fair.
Thank you so much.
Grad alpha is, or sorry, alpha itself is just an angle, and I've purposely shied away from the underlying representations here. But we just have an angle at every point. Grad alpha is the direction of the biggest increase in alpha, so it's the direction along which alpha rotates counterclockwise the most. So here we have, it's technically 4 directional derivatives, but if we just look at tau, for instance, we have the gradient of tau, and let's migrate tau itself over. So we could say the gradient of tau over tau in the direction of alpha is grad alpha in the direction across from it. So all of these are relative changes in size.
So like the parentheses indicate like a function input, not a dot product.
No, so sorry, this is a dot product. We're taking the angle alpha and turning it into a vector. So the second equation is we have the gradient of tau, but if we dot that with a vector, we get the change in tau in a direction.
Direction of the
Right.
direction.
Yes. Okay, sorry.
Sorry, I just had a question at the very beginning of the talk. You said that you were motivated to look into this by groundwater. How are crossfields connected to groundwater in California?
So, actually, to go back up, so we started off working with the Department of Water Resources where they use triangle to generate meshes. And in particular, they have the boundaries of their region are like on the order of counties. But they wanted to explicitly look at groundwater flow around wells. So they wanted a huge difference in size. And Triangle was working really well for them, but they heard about this magic technology called a quad mesh that uses fewer elements. So we started off just trying to find a consistent quad mesh that covered the region. But we're looking into sizing. And anisotropy was actually rather unexpected because the size functions we were looking at, we were saying, go from 1 to 4. That should be a nice isotropic size function. We should get a crossfield out of it, and that crossfield should be isotropic. Everything should be good. And none of our metrics were working. So yeah, the goal is to have as few elements in the mesh as possible, because in a lot of cases, I was working with people who had to use their personal laptop to do like a groundwater simulation. So like the fewer elements we could get in the mesh, the happier they were. So, but then that went into trying to do size-aware crossfields into size-aware meshes, and this is where the rabbit hole has led. So.
Thanks, that's really interesting. And just one more quick question. So here you're trying, or at least your optimization is trying to make things as isotropic as possible. If you had some target anisotropy that you wanted, would it be as easy as like swapping out the 2 in your objective function with something else? Or how much would things change?
So if you had a targeted, oops, way too far. So this 2 was just to make the energy function go to 0 for the isotropic case. You could, like if you had a target anisotropy at a point, yeah, you could replace the 2 with the target anisotropy and get that same behavior. But because we have so many degrees of freedom, if you had like just one point that you were looking at, it might be easier to just fix that point and see what the solve does everywhere else. But yeah, that would work.
Okay, I think we ran out of time for questions. So let's thank the speaker again.
So I'm here to talk about a work about optimizing dual volumes for tetrahedral meshes. So discretizing integrals over volumes is a fundamental operation that we do in geometry processing. If we have a tet mesh representing the interior of a shape, two very important integrals that we would like to be able to do on that tet mesh is integrate up the squared value of a function. In the discrete sense, this looks like having a vector of values f at each vertex and multiplying it by a mass matrix and then by itself again. Another fundamental integral is the Dirichlet energy, which integrates up the squared gradient of a function over the domain. And this looks like minus, to choose a convention, minus that vector f times a Laplacian matrix times f again. The standard way to discretize both of these to get both of these matrices as a discretization for tet meshes is to use linear finite element method. And I'm sad to break the news to you that this is really flawed for tet meshes. And it gives really surprisingly bad results on simple problems. So here is a regular grid where each cell, each cube of the regular grid has been broken apart into 6 tetrahedra in the obvious way around the main diagonal. And I'm solving for an eigenvector using those two matrices. And we'd expect that all the eigenvectors for a simple shape like this, this box shape, would be symmetric. It wouldn't see the difference of the choice of tetrahedralization. But if we tetrahedralize each cube on a different axis, then we get a completely different result, and we get bias based on the connectivity of the tetrahedralization of this grid. Finite volume method is an alternative to the finite element method, and one way to understand how finite volume method works is to think of it as discretizing the integrals by breaking up the domain into small local regions around each of the vertices or each element in the mesh. This is easier to see in 2D right away, so I'll show you for a triangle mesh first. So you see the triangle mesh, and then overlaid on top of it is the Voronoi diagram of each of the vertices, and this is one particular way of defining those local regions that I'll call star I. They're dual to the points of the triangulation. So the points are 0-dimensional and these regions are 2-dimensional. And once we've defined these regions, we have one for each vertex, so that's my star I for that particular vertex. Then I can go about discretizing those integrals that I mentioned before, and I'll get into that in a little bit. So finite volumes work really well for the regular grid if we use these Voronoi type of dual volumes. So they're completely unbiased for the regular grid. We get exactly the same dual volumes regardless of the tetrahedralization of that grid. And we get a perfectly symmetric solution. So it seems like things are really good using finite volumes and the Voronoi diagram. But the problem is most of our meshes are not actually Delaunay meshes, which have this great duality with the Voronoi diagram. So if we use the same construction rules on a non-Delaunay tetrahedralization, we will get volumes, local volumes. This is the local volume around a single vertex, and it's a horrible hot mess. We have positive regions, regions of positive volume in pink, and we have regions that have flipped inside and prolapsed outside of itself that are now negative, and those are the blue regions. And these are going to cause all sorts of problems when discretizing the integrals. In particular, when we go to write the mass matrix, which is simply the volume of each of these local regions along the diagonal, we could get negative values, or we could even get zeros. Our matrix could be singular, and everything will blow up. I did some quantitative study taking the meshes that are output of Tetwild on the Thingy 10K data set. And yeah, most of these are not Delaunay meshes, even though this is a meshing program that's trying its hardest to make really high quality triangle meshes. So more than 50% of the tetrahedra are outside, their circumcenters are outside of themselves, so that means that they are not locally Delaunay. And if we even look at the subsimplices inside of the tetrahedral mesh, so the triangle faces on each tet, then things are also very bad. So in the paper at SGP this year, I've analyzed different methods for finite volume construction and shown why they fail on a couple of different criteria. One particular choice for finite volume method coincides exactly with linear finite element method, and that will be, I'll call that barycentric, and we'll see in a second what that looks like. One nice thing about here's animation of changing a tetrahedral mesh and showing the finite volume around some vertex. And we can see that it changes continuously with the change in the vertex positions of the tetrahedral mesh. But we saw that it performed badly on a regular grid. So I put an X there to indicate that it's biased on that regular grid. If we use the Voronoi diagram, or its equivalent choice of circumcentric dual volumes, this is also continuous, but we lose the property that all the masses are positive. And for the Laplacian, things are also bad. We don't get a semi-definite Dirichlet energy. In the literature, there are previous proposed fixes for this problem of the circumcentric duals. And unfortunately, what we see is they give up one property in favor of another. So for example, Alexa and colleagues a couple years ago proposed a fix for the circumcentric duals, which make all the volumes positive, but this makes it no longer continuous with respect to vertex positions. And here's an example of that. So we're deforming the grid, and when the grid gets too stretched out, things snap and that finite volume changes shape dramatically. So what I'm going to present today, after a little bit of analysis, is a method that meets all the criteria that I've set out, and we see that change here as the tetrahedral mesh is changing, the finite volume is adapting to the change in shape, and it does so continuously. So let's dive into these integrals and then take a look at specific choices of finite volumes. Let's start with the easier one, the sum of squared values. So in the continuous setting, we're writing this as an integral of the function value squared. We can understand this as a quadratic form as f transpose mf. We can also understand this matrix as a linear operator. And we can ask, when we multiply m times f, what does it do at a particular vertex value I? So I represent this to mean take the ith value of what's inside of the parentheses. And this is really just asking what is the sum of the value f inside of my region, or really what is the mass of that object. And if we look at the volume around a particular vertex, I'm going to make a choice here, like most of the previous finite element methods, that we only consider mass contributions by neighboring tetrahedron. So each tetrahedron contributes some of its mass to that vertex, and I'm referring to the primal volume of a tetrahedron using this dark circle. So tetrahedron number 1 contributes part of its volume to star I, meaning the dual volume at I, and so does tetrahedron 2 and tetrahedron 3. So then we can say the entry in this mass matrix, which is diagonal, is simply, at the ith value, is simply a sum of the contributions made by each of the tetrahedra incident on that vertex. Finite volumes discretize the Laplacian in a sort of different way. Oh, one thing that I wanted to point out here is that when we discretize the mass matrix, we are making an assumption that our function f is constant inside of the dual volume. And that choice will be slightly different, and it's kind of weird that it's different when we discretize the Laplacian, but that's the world. Okay, so let's try to discretize the Laplacian. Again, we can see this as a quadratic form, and when we write it as a quadratic form, it's not necessarily immediately obvious why I'm calling this thing Laplacian if I'm seeing two gradients here. If we apply Green's identity to the left-hand side, we can move one of those derivatives onto the other guy, and we get f times its Laplacian with a minus sign out front, and we also get boundary terms. And for now, we will assume that those boundary terms go to 0, which is the natural thing to do in this case. If we see this quadratic form, we can equivalently look at the linear operator view. So now we're looking at what does L do when you multiply it by f at a particular vertex. Again, we'll take that local volume around a particular vertex, and we can write a contribution of each of the tetrahedron to that vertex's value. And what we're looking at is the integral, or the sum, of the Laplacian of f inside of that volume. And here it looks a little tricky, but we will have Gauss to our rescue and apply divergence theorem. So now, instead of integrating inside of the volume of this local region, we will integrate over the surface of that region, so along the faces. And we'll make a slightly different choice about what's happening with f. Now what we will assume is that f has constant gradient inside of each of the tetrahedron. So it's not constant gradient inside of the entire local volume, but on each of the contribution pieces, it has constant gradient. And this allows us to pull the integral outside. And now if we have a closed form expression, or if we have an expression for the surface here, we can compute this contribution directly. And each of the pieces here just represents a chunk of the surface, or the faces that the colored faces that you're seeing here. And at this point, now the Laplacian is fully determined if our local volumes have been determined. So that's great. So let's look at different ways of choosing these finite volumes. The existing methods that I consider construct the contribution for each tet to each vertex by making a decision about centers for each of the subsimplices. So we have the vertex as kind of the zero center of itself. Each of the edges has some center. For now, you can just think of these as the centroid or barycenter. Each of the faces, or the triangles around the tet, has some center, and the tetrahedron itself has a center. Where the methods disagree is how exactly to define these centers. So the most obvious or simplest choice is to take the centroid or barycenter, and this results for a single tet, we see something like this. So this finite volume is nicely behaved, or it looks very natural. And if we see how this shows up for the mass matrix, what we end up getting is that the mass matrix is simply an average of the tetrahedron volume's contribution around it. So each tetrahedron contributes 1/4 of its volume, regardless of its shape, to each of its vertices. The Laplacian can then be broken apart, how we saw before, into per tet contributions. I like to see this kind of from the finite element point of view, where we say that the Laplacian, the energy defined by the Laplacian, can be rewritten as a sum of that energy over all of the tetrahedron, where what we do is we suck out the 4 corner values on either side, and then define a local energy on the inside. So this S matrix here is just extracting the 4 corner values on the tetrahedron T, and then the LT is a 4x4 matrix that computes the contribution of that tetrahedron to the total Dirichlet energy of the entire mesh. We can further break down that Laplacian LT into the gradient portion. Remember, we said that the gradient was fixed or assumed to be constant inside of every tetrahedron. So regardless of the choice of centers that we have for finite volume, this GT matrix is just fixed. So the degree of freedom that we have here is in the DT matrix. And I've called this D to allude to the fact that we can think of this as a divergence operator. If the Laplacian matrix should be symmetric, and it should be symmetric for every tetrahedron, which not all the methods will actually do, but if it is symmetric, then DT must have the form GT transpose times AT, where we can think of this AT matrix, which is a 4x4 positive semi-definite matrix, as a 4x4? 3x3. 3x3, I'm sorry about the typo. This is a 3x3 matrix that we can think of in an FEM point of view as a diffusion tensor. So when we choose barycenters for the finite volume, essentially what we are doing is just taking the area of that tetrahedron and multiplying it by the identity, and that is our diffusion tensor that we're using. And this is exactly how, at least I can see why barycentric finite volumes perfectly coincides with linear FEM, because we're just saying take the gradient and square it and integrate it in the FEM sense. And we saw before that linear FEM is giving us bias on the regular grid. And if we look at the finite volumes around each vertex on the regular grid, we see that they are not symmetric, and they definitely depend on the connectivity that we have in each of the cells. So the difference between these two images is which way each of the cubes is tetrahedralized. In contrast, if we switch barycenters for circumcenters of each of the sub-elements when we construct the finite volumes, then we get this perfect unbiased behavior on the regular grid. We can take that circumcentric dual volume and kind of reverse engineer this AT matrix that for barycentrics was just an identity. And if I didn't mention it before, but sorry, these were visualizing that diffusion tensor sort of applied to a sphere, so they just stay spheres. If we take the diffusion tensor for the circumcentric duals and apply those to the sphere, we see these ellipsoids. So in this way, we can understand the circumcentric finite dual volumes as kind of manipulating the diffusion tensor per tet and then just applying linear finite element method. The problem that we said before, the reason the story doesn't end here is that these circumcentric duals perform really badly on non-Delaunay meshes and give us these negative volumes. Here's what it looks like for that tet as it's moving around. So it looks nice until the circumcenters sort of flow outside of the shape, and then we get these negative regions in blue. So the idea is quite simple, to snap these somehow and keep them inside of the darn tet. So Alexa and colleagues proposed snapping these bad circumcenters to the barycenters of the corresponding simplex. So we can see as one of the vertices moves close to the boundary, it kind of pops back inward. This is good because it keeps the volumes positive, but it's bad because it doesn't necessarily result in a symmetric contribution to the Dirichlet energy for that particular tet. And this poses problems in downstream applications. So if we took an eigen decomposition of the Laplacian for a particular tet mesh, like this Fox shape, we expect that the direction that corresponds to the smallest eigenvalue is a constant function. But if we take a Laplacian matrix constructed with the snapping of Alexa and colleagues, we get something that could even have a negative eigenvalue for a non-trivial function. And since all the other eigenfunctions will then be orthogonal to this, this can break down further applications. And then maybe the most obvious thing that we see in this animation is that it's not continuous. So we see popping around and the volume is changing with respect to the tet vertex positions. And I think that the key problem here is that as a circumcenter is leaving its corresponding subsimplex, it does not exit through its barycenter. It actually exits through a circumcenter of some yet other subsimplex. And so a natural attempt at a fix here is to snap to the subsimplex's circumcenter. And here we see a continuous change. So if we watch sort of the tetrahedron center in the middle, as it passes out toward the triangle, we snap it to the triangle's circumcenter, and if even that then left the triangle, we could snap it to the edge's circumcenter. And once we get to edges, all the centers are the same, barycenter and circumcenter. This seemed like a good idea. It's always non-negative and it's continuous. Unfortunately, and I really wish it was the case, but it's not going to give us a symmetric Laplacian. And that's sad, but we're just going to have to deal with it. And we're going to deal with it in a really dramatic sledgehammer-y kind of way. We can prove that this is not symmetric by extracting that AT matrix and then looking at it and see, like, does this give us a positive definite matrix? And it doesn't always give us one. The key idea of what I'm proposing is pretty dramatic. I'm just going to optimize for the circumcenter, or for the centers and make sure that this AT matrix is always positive definite. So I set up a loss function that minimizes the square difference between the centers and their circumcenters. That way, if the circumcentric dual volume is good, it's feasible and gives us a symmetric thing, I'll just return that. But I'll also add some constraints. One constraint is that each of the centers stays within its primal volume. So for faces, the center should stay within the face. And then another constraint that this AT matrix, which fortunately is a linear function of the center positions, this matrix should be positive definite. This is a strictly convex semi-definite programming problem, which means it has a unique global minimum and it's a continuous function of the vertex position, so that's great, it's C0. The mass matrix is always positive. The Laplacian by constraint is always defining a semi-definite Dirichlet energy. And if, like I said, if the circumcentric dual is feasible, then we'll find it. And since the circumcentric duals are feasible for the grid, then we get an unbiased grid result. So we've hit all the properties that we want. I have a conjecture in this paper that it's enough to just require symmetry of the diffusion tensor. I couldn't really prove this in an elegant way. I fed it through an SDP solver for a particular TED, and it showed that the problem was infeasible, which corresponds to not finding a counterexample. This is sort of good because SDP problems are pretty slow to solve, and QPs are also pretty slow to solve, but like not that slow to solve as an SDP. In the worst case, what you can do is run the QP, check if it's feasible, and if it's not, run an SDP solver to polish it up. I don't want to show the timings, they're embarrassing. You can look in the paper. The Alexa and colleagues paper had this nice experiment where they demonstrated the power of the circumcentric duals by showing that it has lower variance. This is kind of like a generalization of not being biased on the regular grid. You can show that this pays off for other tetrahedral meshes. In that paper, they only showed the barycentric and the circumcentric dual volumes. I also computed that experiment for the snapping proposed in that paper and for the optimized centers in this paper. And I was pleasantly surprised that the optimized centers from the SGP solve closely track the circumcentric low variance results, which is great, and you always get positive volumes. Another application is to consider a setting where you're bringing your tetrahedron mesh along with you during a design process. So Adriana Schultz had this paper at SIGGRAPH where they bring a tet mesh along while they're doing interactive CAD design. In this case, you would want that the operators that you build on your tet mesh are a continuous function of whatever you're doing in your design, so that if you were like backpropping gradients through this whole thing, you get continuous evaluation. If you use a discontinuous function for discretizing those operators, then you get noise appearing in all the discontinuities. And it was actually surprising just like how much noise there is for a moderate-sized tet mesh, because basically at any small change, one of the tets in your system could be popping to a different volume. And our optimized results are, you can kind of see the kinks, where you can see that it's C0 and not smoother than that, but at least it's a continuous function. Okay, so in conclusion, I'd like to propose this SDP optimization as an existence proof of finite volumes that satisfy all the properties that I set out for. Anytime you see a feature grid, you should always ask, what's the missing column? Like, what is the thing that I've been hiding from you and like my method doesn't have that all the other methods do? It's clearly speed as one of them. Like, this is way too slow just to compute a Laplacian or a mass matrix unless you have a reason that would amortize or you badly needed these properties. But I imagine that there's other properties that would be important here. Like one thing, for example, is that the quadrilateral faces of each of the hex contributions are not necessarily planar in my discretization. So maybe looking for planar ones that still meet these other properties would be great. With that, I'd like to thank my funding agencies and the people that made the models, and thank you all for your attention.
Questions from Mark? So this is the point where
people tend to say, you got it all wrong. No, I think you got it all right. And I don't think there is a missing column. I mean, this is more a comment, yeah? So there's an interesting, so my question would be, how does this relate to weighted Delaunay triangulations? And why don't we see the limitations that Max, Wadetsky, showed there should be? But I also have the answer. So that's my congratulations, right? And I'm sort of embarrassed that I didn't see this. So not every tetrahedral mesh is a weighted Delaunay triangulation. But every simplicial mesh in dimension larger than 2 is a power diagram. So by going to the dual volume, in dimension 3 and higher, you can really construct perfect Laplace operators. And you found it, right? So, thank you.
Well, thank you. I mean, I hope, like, one, I hope, like, we can, there is something positive in this proof about just constraining symmetry, and maybe there is some trick with parametrization. We can find these faster, and maybe even if we have to solve the SGP, we can do some kind of ADMM or something that, like, very quickly identifies these so that we're not seeing those embarrassing timings compared to just running a for loop.
Yes?
I'm wondering if somewhere in your algorithm you numerical quadrature you integrate
Yes. So the question was, do I use numerical quadrature in the algorithm? Yes. So in the construction of the, so like if you're asking about like my optimization for the centers, I don't really need to use quadrature. The only place that it would really show up is, well, okay, I guess there's like two different views. Each of the contributions inside of a tet is a small triangulated polyhedron, and you can either go about computing its mass or the integral of its normals over the surface like purely geometrically by just like kind of working out a bunch of triangle stuff. Or you can look at it and say like, this is a this order polynomial, and if I use this order quadrature, I can compute it exactly. I kind of come from just like heritage reasons. I would do it like by messing around with triangles, but other people would look at these and just apply quadrature rules. So for that part, that's kind of interchangeable.
Okay, yeah, thank you.
Sure.
Thank you for the talk. It's really remarkable to see how such a simple example on a box is so biased by this seemingly innocent choice of diagonals. Do you know what happens if instead of using linear, you go for higher order FEM?
Yeah, it's a great question. I don't know if I didn't try it. My guess, based on looking at these like diffusion tensors, is that it just gets mitigated and it doesn't go away. I'd love to try it and see, but I don't see why this just like suddenly vanishes from the like diffusion tensor point of view. Because it really looks like, when you look at that G transpose AG, like the G's are so innocuous and innocent, and the A is just this identity matrix. Like I don't see like why adding like powerful polynomials on either side necessarily fixes it. But it's a great experiment to do, and maybe with poly-FEM it's easy to do.
Yeah, this seems to be something
cool.
Easy to run, and I agree. I also think it's gonna go away, but it will be curious to see what it does.
Thanks.
And maybe like another follow-up, since I have a microphone. Do you know what are the conditions on the mesh to actually guarantee that the problem has a solution? Or does it always have a solution?
Yeah. It just has to have, so this is actually a nice thing I didn't talk about in the talk. As long as the barycentric solution exists, I'll at least find that thing, right? Okay. So like, and that's, I think that just means no subsimplex degenerates, right? So like the tets have positive volume, and that's enough. Yeah, because like that's a feasible, it's not a good solution, but it's a feasible one, so I'll at least find that one.
Thank you.
And that's probably, if I was using an interior point solver, I'd probably start with that one as a feasible guess.
Thank you. From purely technical perspective, since the faces of your dual cells are not flat,
yeah,
How does that affect computation of the stiffness or the Laplacian?
Oh, I just triangulate them, and they're quads, and I pick a triangulation.
And does it make a difference, or is that?
Not really. I mean, it doesn't make a difference in the circumcentric case, since those are planar. So where it would show up is when we go outside of that case. In some cases, I think, like in this case, the skewing is so regular that they do stay planar. They definitely are not always planar. Like there are cases that they're not planar. And at some point I had these dreams of like doing some discrete optimization on top of this to like choose the triangulation, and I never did that. And maybe there's like an even fancier thing where you use like bilinear patches or something like that, but I didn't try it. Yeah.
Yeah, so just out of curiosity, going off on these other columns, so Delani refinement for type meshes has quality and performance guarantees. If you run Delani refinement on a set of mesh with the angle bound that you get, do any of these other columns or these other strategies now have check marks and all that? So what I'm saying is, you sort of sidestep this when it's reprocessing the mesh or running Delani refinement.
Yeah, I don't think so either. Like for barycentric or linear FEM, I'm sure you can like drive the grid biasness to 0, but like I think it's only going to happen in the very limit. Like that's going to have some convergence to 0. For circumcentric,
Sorry, I don't follow. So again, if you have these angle bound guarantees.
well, like suppose you have a grid. So like the grid column is like, I have given you a cube of a grid, and I've triangulated it, and now you should give me a solution that's symmetric and shouldn't care about the connectivity. So if we say that we're like also refining on top of that, it's kind of shifted the game a bit. So I'm not sure exactly what that column looks like for a method that's allowed to refine, or for example, a method that's allowed to do P refinement. But my guess is that if you were limited to doing like refinement that stayed on a grid, you'd still have this problem. So just like subdividing the grid doesn't make this go away. If it's like doing Delani refinement on that initial mesh, I think it also probably goes away. I guess if you did like Delani refinement up to some angle, maybe it goes to 0 at some point, but I can't, like if you're asking me to guess, I guess no. And then for circumcentric, I don't have a better intuition for that, but like, again, it's kind of like shifting the game. Like there are also these like Hodge optimized triangulations where they do primal and dual optimization. You can see my method is just doing dual optimization. Those do have, like when they converge, they work better. And Fernando sent me an email saying that there's a convex version that always has a solution, and maybe that's true, and then that could be like a continuous one, but they're changing both of them.
Any more questions from the audience? Okay, I actually have a question. You kind of started answering, but maybe, so the equivalence between linear FEM and barycentric finite volume is because the gradient is constant per text, so this integration works. So you actually modulate this constancy by some kind of diffusion tensor. Can it reflect back to a linear FEM to make FEM that is something else? Like in case you want to talk about like the vector field, the gradient vector field or something like this.
So it's still constant in each TED, because
The metric is different.
the metric is different from just like the identity metric. So that's how I kind of understand like what is, I don't have like a good intuition of finite volume method, but I have a pretty good intuition of FEM. So like the way that I see these is like they are changing the way that I'm deciding how things diffuse in each TED, and then I just run linear FEM on those. So like I do kind of like interpret this as like, what is the way that we like skew or distort FEM to give us better behavior on a particular grid without changing the grid? So like the game is like you're not allowed to change the grid, which like you could just argue that that's silly, like just change your primal grid.
This can bring a full suite of operators like gradient divergence, otherwise in this closed form Laplacian kind of thing. Yeah.
Yeah, I guess so. I mean, like, why not define that divergence in terms of like pushing half of that matrix on either side?
And then by
Yeah.
joint, you can-
Yeah. Like basically factor out the identity with the volume and yeah.
So let's.
Thank you.
Alec and the rest of the speakers.